Welcome and thank you for downloading this TU Delft podcast.
Hello, I am Gerard van Bussel and I'm a professor in wind energy at the Faculty of Aerospace Engineering of Delft University of Technology. I would like to tell something about the aerodynamics of windmills and wind turbines, which is quite a complex phenomenon. We will start with some history, and actually the history on windmills started something like 3,000 years ago in an area we now call Iran, Persia. There you had already some rather simple structures that used the wind to rotate some stones, and in between stones grains were grounded. This is a picture that gives you a little bit more detail about this system, and it factually consists out of a number of vertical plates which are blown away by the wind. Using the wind to blow plates away is a possibility to extract energy from the wind. But you can only extract energy if the plate is moving. So whenever you have a plate at standstill, you have a huge amount of force, but nothing is moving. So you do not have power that can be extracted. That means that you need to have some movement, some displacement of the plate in order to extract power. When you do that, then again you have a disadvantage, because if the plate moves with the wind, it means that the forces on the plate are reducing. The power can then be easily calculated by a multiplication of the movement velocity and the force on the plate. But we can get plates working in a different fashion. Let's start again with the plate at standstill, but now we take the same plate and we just tilt it a little bit. Then you will see that apart from a large force in the direction of the wind, you have a small force in a perpendicular direction. That's a force that we call lift. So far, so good. But what can we do with slightly tilted plates? The same picture again, a force in the direction of the wind, which is called drag, and a small force perpendicular to that, which is called lift. When you now take this plate and tilt it almost completely to, let's say, something like an angle of 10 degrees, then suddenly the drag gets a lot less and the lift gets a lot larger. In fact, if you don't believe this, you can go to a do-it-yourself shop, buy a kind of plaster plate and try to find out what the forces are when the wind is perpendicular and when the plate is almost parallel to the wind. And you will find out that the force in that situation is almost the same as the force perpendicular to the plate. That is what we call lift. So now we have a large lift and a rather small drag. This is the starting point for the understanding of the aerodynamics of modern windmills and modern wind turbines. Again, this is the slightly tilted plate, and now from looking to this from a situation in which the plate is at standstill, we have a plate which is moving or rotating. And when you put a rotation on, then on top of the velocity that you have from the wind, you also have the rotational velocity. Those two end up with a total velocity which we call the resulting velocity. And again, when that is under a rather small angle of, let's say, 10 degrees, then you end up with a huge amount of lift. And that huge amount of lift, that's the key issue, so to say, for understanding the aerodynamics of wind turbines. Because this lift is proportional to the square of this velocity. So that means, for example, that if your blades are rotating with a speed which is 5 times as fast as the wind, you end up with a force which is 25 times more. Okay, this is something that was already discovered in the beginning of last century in Europe, where we developed our own Dutch windmills. This is one of the first pictures of a Dutch windmill where you can see 4 sails. If you follow the pictures in history from 1217 up to the 16th century, then you'll see something strange, because in the first picture, that's the picture on the right, you see that the blades are symmetric. On the left-hand picture, that's still the case, but if you then continue to a little bit further away, you'll see a shift, so to say, of the sails, which is not symmetric anymore. This is easily illustrated from this picture, where you see some cross sections through the blade. So in the early days, the blades were symmetric, and then gradually they moved from a symmetric position into a position where the main spar is actually on 1/4 of the blade, and 3/4 is on the other side. This is the same picture again, and it's again a cross section to one of the blades of an old windmill. This ends up to be a rather primitive, but still an airfoil, with all the normal forces that you have on an airfoil. So this old sail just works like a modern wind turbine blade. And here is what you can see. You indeed see that although the forces might be slightly less, the distribution of the forces is just as if it is an airfoil, a classic airfoil, but an airfoil. So in other words, the operational principle of our Dutch windmills is exactly the same as the operational principle of modern wind turbines. Apart from thinking in terms of lift and drag, you can also think in terms of thrust and torque. Thrust is actually the force that the wind applies upon the wind in the direction of the wind, and the torque, that's the component of the force that you use to extract the energy. This is an example of an experiment that was done some 10 years ago in a large wind tunnel in the United States. The NREL did the experiments in the NASA Ames wind tunnel. On your left-hand side, you can see the wind turbine rotor in the test section of the wind tunnel, and on the other side you see a smoke visualized flow. In this case, there's a grenade, a smoke grenade, attached on the tip of the rotor blade, and by doing that you can really see what the traces are, so to say, of that vortex into the wind. In Delft we've done similar kind of experiments, but in that case what we did is we emanated the smoke into the flow at the beginning of the wind tunnel. That's basically something that you can see over here. When there's wind, but when there's no wind turbine, then the flow would move completely horizontal. In this case, we have a system in which the wind turbine is actually in operation. Let's go to the next picture, and there you can see what's going on. So we have a thrust on the rotor. There's some force acting upon the rotor. The force is on the rotor, and of course then action is reaction. There's a force that rotor applies against the wind. As a result of that, what you see is that the flow is now not moving horizontally anymore, but it's deflecting. So it's deflecting from here downwards. And that is pretty important. So actually, because this rotor is not really blocking the air, but it's retarding the air, you have a flow, an incoming flow, that sees something which is not a solid building, but something that tries to break it. And of course the wind then tries to escape. Outside of this system, you of course have a flow which is virtually undisturbed. But inside, that means the air that is going through the rotor is retarded, is slowed down. And what I've shown here is actually the optimal situation. And the optimal situation is such that, of course, in front of the rotor you still have the undisturbed speed, but when we go down, then in the end you end up with 1/3 of the speed that you had in front. What you can also see is that part of the air that's coming from the wind tunnel, that's the part that's over here, is now escaping. It's not going through the rotor anymore. The conclusion is then that the mass flow through your rotor, so that's the mass flow through this area over here, is only 2/3 of the mass flow that you think you can capture, because 1/3 is in fact escaping over here, from here, underneath the rotor. And then what you can see is, because the end velocity is 1/3, the amount of energy that you can extract from that mass is equal to 1 minus 1/9, which is 8/9. So from that 2/3 of the mass, you extract 8/9 of the kinetic energy. That is all you need to know to understand the aerodynamics of modern wind turbines. Because if you try to increase the force, you will see that your mass flow will reduce. And when you reduce the force, of course, then you have an increased mass flow, but then the amount of energy that extract is less. This is the optimal situation. Here. So here we have the optimal situation where 2/3 of the energy is extracted. 2/3 of the mass flow is processed, and from that mass flow, 8/9 of the energy is extracted. That forms the basis of the theoretical maximum power that can be extracted, which is indeed 2/3 multiplied by 8/9. So 16 divided by 27th of the amount of air that you have available, it can be used for energy extraction. If you compare that to the system that was used in Persia, so that was the plate that was moving with the wind, then you come to the conclusion that the maximum amount of power that you can get out of that is only 5 divided by 27. Which means that propeller type wind turbines, and even our old Dutch windmills, they are at least 3 times more efficient as the old Persian ones. There you see why nowadays we are using modern versions of our old Dutch windmills for energy extraction. So in other words, these kinds of drag-driven, as we call them, wind turbines, although they look different from the old Persian machines, they have the same working principle and therefore they have a low performance. Where the modern wind turbines, and then it does not really matter that much how many blades you have, they have a high performance. Well, then what about the difference between a 2-bladed wind turbine, a 3-bladed wind turbine, or a multiple-bladed wind turbine? Well, here I've summarized some of the characteristics of the different wind turbines. If you have a 2-bladed wind turbine, then you have a very low torque with a very high rotational speed. Whereas if you have a multiple wind turbine, it has a high torque, but it rotates very slowly. This is what you can see over here. In the end, it does not really matter how many blades you have. You have exactly the same power that you extract. The reason for that is that it only matters how much thrust force you apply. The thrust force should be optimum, not maximum. Here you can also see that if you have, for example, a 3-bladed wind turbine, and you add some extra blades because you think that's going to give you more power, that doesn't hold. The only thing that will happen is then that that wind turbine will rotate more slowly, but it gives you the same amount of power. Okay, why would we try to use 2-bladed wind turbines? Well, 2-bladed wind turbines are nice because they're cheap. You need to manufacture only 2 blades, and its rotational speed is larger, which means that you need a smaller gearbox. I think that we will see 2-bladed wind turbines again in the future for offshore applications. On land, we usually see 3-bladed wind turbines. Why? Well, because 3-bladed wind turbines, they rotate slower, so they make less noise than a 2-bladed machine, and they look better, they look nicer. Those are the 2 main reasons why onshore we see only 3-bladed wind turbines nowadays. Well, why then multiple-bladed wind turbines? Well, because sometimes you need high torque, for example, for pumping. And therefore, if you want to use wind energy for pumping, you have high torques, a large number of blades, and a low rotational speed. So this is where we are ending up with, a modern onshore wind turbine having 3 blades, and actually these blades have airfoils that are no longer taken from the aerospace industry. They are dedicated, designed for application on wind turbines, and amongst others, we do that at Delft University of Technology. Well, what about the size? Well, the sizes up to the end of the 80s were in fact similar to the sizes of our old Dutch windmills, which means we had diameters of, let's say, 30 meters, more or less. Then from that point on, 1 decade later, we saw already a big decrease, because in the end of the 90s and beginning of last century, beginning of this century, we already built wind turbines that have dimensions, which means a span of the rotor, which is equal to the A380 Airbus. That means something like 80 meters. And as I said, this was about 10 years ago. What we have nowadays are giant wind turbines. And these wind turbines are majorly designed and manufactured for operation offshore. And they have a size which is so huge that the total swept area is almost equal to the size of 2 football fields, 2 soccer fields. It's hardly to imagine how that looks. But I can show you, because this is a picture of the largest blade. And if I'm going to stand over here, you can see what happens when a truck with such a blade passes you along a road. It's huge, isn't it? Okay, in fact the same holds for the increase of capacity of wind all over the world. What we have seen is, over the past 20 years, a 30% increase each year of the capacity. That means that every 3 years we have a doubling of the capacity. And at the moment we are around 100, you can see it over here, 175 gigawatts, which actually means that the installed capacity is the same as, let's say, 160,000 megawatt power stations. So we have 157 power stations up and running, and next year it will be 30% more. So it goes very fast. Well, why are we working on wind energy? Because the cost of production of electricity from the wind is already comparable to the production cost of gas, of coal, and of nuclear. And it's of course the most environmentally friendly way of producing electricity, with a very low greenhouse gas impact and a very low impact in terms of small particles. So wind, I think, is the energy source for a sustained future.
Please visit our OpenCourseware website for more information. See you at our next podcast. Welcome and thank you for downloading the Delft podcast.
Hello, I am